Okay, this is
您清楚
YOLO
知道自己
V2.
的理想。GoDaddy 拥有丰富的网域。
This is YOLO V2. So before we continue, what's the difference between detection and classification? Here's one. So what's the difference? Okay, so classification, what we have learned so far is our classification. For example, we learn how to classify images in image class in ImageNet. There are 1,000 categories in ImageNet. In fact, detection is a binary classification because it wants to classify if an object exists or not. Also, it can be viewed as a binary classification. So it's a very traditional research topic because we always want to know. We always want to identify the object first and then apply more advanced computer vision algorithms, right? So I start with some famous object detection models during the last decade. The first is the deformable part model. It's still quite accurate, but it's before the deep learning era, or it's the best model in 2010. And then the fast RCNN model is after the deep learning has been proven the work, the performance is outperform other methods. Then researchers start to use the deep learning model in object detection. Remember, it's around 2012 that the AlexNet has been released, right? AlexNet has been released in 2012. So after 3 years, it's finally researchers can apply the deep learning in object detection. So the first version is the fast RCN, and the second is the faster RCN. And actually, there's a trilogy of RCN, fast RCN, and the faster RCN. And then now YOLO has been announced. Now YOLO is, we can say, it's the most popular framework. So far, it has achieved very good performance. YOLO is called You Only Look Once, or You Only Look Once, so real-time object detection. Okay, another good model is SSD, a single-shot multi-box detector, SSD detector. And another important task is the RCNN, mask RCNN. Remember, we have 4 different tasks for computer vision, right? I think I should add this page. The first is classification, the second is localization, the third is object detection, and the fourth is segmentation, right? Segmentation wants to segment, to identify each pixel, identify the class of each pixel. So it's the most difficult task, but very important. And YOLO now, since YOLO has been announced, it becomes very popular, and there are a lot of different versions to improve the speed and accuracy. On the second version, YOLO V2 is called YOLO 9000, which can identify 9,000 objects. However, only a few objects are accurate. And the V3 is an incremental improvement. After that, another author other than the founding author of YOLO, proposed new architecture. Among them, YOLO V4 is actually proposed by Taiwanese, Taiwan PhD called Wang Jianyao. He is quite famous in Taiwan now. So he proposed the YOLO V4 before. And YOLO V5 was proposed by a company. It's a commercial product. So I don't know. As far as I know, you can only get the pre-trained model or something else. I'm not pretty sure. I heard it's proposed by a company. For some tasks like the pothole detection for autonomous vehicle, V4 has been shown that has been reported V5 has better performance than V4. But generally, V4 has a lot of new versions now. This year, they proposed a new V4 version which can detect small objects very well. Okay, so before we continue, we want to talk about what is objectness and the selective search. The objectness is to find the area that could include find the area that has highest probability to include objects. So it's called objectness. The objectness. Okay, here's an example. So objects have some visual features. For example, they may have some closed form, right? And they have some spatial features and some textures. If the area that has a high smooth texture is highly possible it belongs to background. So we can train a model to identify which part of the image has highest probability highest probability of including objects. This is called objectness. Okay. So there are two famous algorithms that can find the area that include objects. One is objectness, and another one is selective search. This is before the deep learning era. Researchers are using algorithm to find possible areas. So here's our examples. Generally, an object can be anywhere in an image, right? At any scale. So we need to scan all the possible areas in the image. So you will initially find so many bounding boxes. And then we will use some algorithms to combine the bounding box, by the bounding box in the same area, combine bounding box with different scales. And finally, you may get like this. So the selective search or objectness will give you the regions that has highest probability of including objects. Right. This is a woman is in the red, in a yellow area, and here's a photo. Okay, a picture that is in the blue area. So it is also called the region proposal, which means which means to propose the region that contains a lot of objects. So it's called region proposal. Propose the region including objects. It's actually a multi-scale objectness search. Let's run an example. So basically, the algorithm like objectness or selective search will scan all possible locations and scales for location regions contains objects. Scan all the location scales for objects. Okay. So the first version, RCNN, is actually region proposal plus the convolution neural network. So it's actually a combination of traditional algorithms with latest deep learning convolution neural network. So for an input image, it first extract region proposals, and generate a lot of proposals, around 2,000 proposals. And then for each proposal, it compute the convolution features for each proposal, and then the rest is the classification. So once they got proposal, they turn the problem into image classification problem. It will be classified as one of the problems. So actually, the detection part largely depends on the region proposal. And it is a two-stage algorithm. Okay, so here's an example for each region. It will generate it will use SVN to classify the image, and also it will use a regression to predict the bounding box size. So in this region, it assumes that there are objects in this region, but it want to find a more precise bounding box. So it will also predict the locations of the bounding box. Okay, so what's there are some drawbacks of the RCNN, although it's very simple and easy to understand. First, there are too many region proposals, and this process is very slow. Running the region proposal, it is slow. It takes around 47 seconds for testing only one image. This is, of course, it's 5 years or 7 years ago, but it's still too slow. This is not because the computing power, but because of the algorithms. So the drawbacks are too many proposals, too slow, and also the selective search is not a deep learning algorithm. It's a fixed algorithm use shadow architecture, so may not be optimized, may not be accurate enough. So I also continue to propose the second version. It's called the fast RCNN. However, fast RCNN is just reverse the order of feature extraction and the region proposal. So previously they run the CNN on the 2,000 proposals, but this time they just run CNN once per image, and then use the proposal to get the region of interest. So actually, there's not much improvement. They just switch the order. In the first version of RCNN, they extract the region proposal and extract the CNN features for all the proposals. So there are a lot of duplicated work. And for the second version, they extract the convolution features first, and then use RI to get the pre-extract features. So basically, there's not much improvement. So I actually think they should not publish the first version RCNN. And okay, so the more important is the faster RCNN is finally replace the selective search with neural networks. So now in the third version of RCNN, we do not rely on the shadow model to find the objectness area. So we replace the selective search. Now we can use neural network to find the region proposal network. So this is the architecture of faster RCNN. Again, we extract the CNN features first, and the features will pass to another convolution neural network, which can generate region proposals. Use the CNN features, and also the feature map has passed. The original feature map has been passed for RI tooling. So for faster RCNN, they use the feature map to find region proposal, but also use the feature maps data as features. And then there is fully connected layer. This fully connected layer will then split into two branches. The first branch is to predict the classes. Is a multi-class classification or is softmax. Okay, remember you need to use softmax for multi-class classification. Okay. And then another one is bounding box. Is a regressor. We will try to output a bounding box that matches the ground truth bounding box as close as possible. So it's basically use, I guess, L2 to calculate the distance. So it's a regression problem. You need to minimize the distance between the true bounding box and your predicted bounding box. So it's a regression problem. Okay. Okay, so now here's a comparison of different versions of RCML. The first one is very slow. The second one is much better. The reason that first one is very slow is that spend too much time on extract CMM features. But the second version is more normal. The latest version is quite fast, which replaced selective search with convolutional neural network. So here's a summary of the trilogy of RCMN. The first one is slow and use traditional selective search to generate regions. It's extract around 2,000 regions and from each image. So this take around 40 seconds to classify one region. Okay, and the second one is much faster because each image is only passed once through the CMM, and the feature maps are extract, and the selection, but it still uses selective search to extract the maps to generate predictions. But it takes 2 seconds, mostly due to the slow process of selective search. The third one is to replace the selective search map with region proposal. The object proposal takes time, but it's much faster, much faster. So it's called faster RCMM. Okay, now let's look at YOLO. You only look once on this very famous architecture. Okay, the first version of YOLO is to divide an image into a 5-to-5 grid. 5-to-5 grid. So YOLO proposed to divide images into small areas, multiple grid. And they will predict the class in each small region, So it does not generate region proposal, but it's forced to divide image into a n by n grid, So it's called you only look once. So first, YOLO V1 divide an image into a S by S grid and predict bounding box for in each grid. So each grid will predict B bounding box and C class probabilities. So each region will predict bounding box at different scales, but it's all inside a region, and also classify the number of class. So for the final prediction dimension, the dimension of the final prediction vector is the number of grid on S times bounding box times 5, because there are 5 parameters. The X and the Y of the X and Y location of the left corner and the width and height of the bounding box, right? The position of the left corner, upper left corner, and the width and height of the bounding box and the components of this bounding box. So there are 5 parameters in one bounding box prediction. The final prediction vector size is s times bounding box times 5 plus the number of class we want to predict. So this is the size of the final prediction, final vectors. Well, B is the number of bounding box. Okay, so although YOLO is very fast, but it sacrifices something, it sacrifices the accuracy. All right. So if the objects are overlap with each other or are very small, then the first version of YOLO cannot identify the small objects very well. So there are some limitations. YOLO intentionally sacrifices some accuracy for its speed, and it's very fast. Okay. So YOLO is quite successful, and then the second version also starts to propose new method to increase the accuracy. So in the second version of YOLO, they propose the anchor box. So instead of predict a prefixed bounding box, or they will try different size of bounding box first and see which bounding box best match the content of the image. See which anchor box best match the shape of the object. Also, it includes the bench normalization in the convolution neural network layer, and it's provide a high resolution, increase the resolution of the classifiers. Okay, so what is bounding box? Bounding box has different shapes because they find that usually different objects have very much different shape, right? The car may have a rectangle, may have a horizontal rectangle, may have a horizontal rectangle, but the human may have a vertical rectangle bounding box, right? So if we apply bounding box, we can first we can detect the objects with different shapes, and more important, we can detect overlapping windows. In this example, in the first version, if we have detect human, maybe we will ignore the car behind the human. But because now we have bounding box, once we match the first anchor, we have anchor box. Once we have find a human using the first anchor box, we will continue to try the second anchor box. And then for the second bounding box, you will find that there's a car behind the human. So in that way, it can detect some overlapping windows. How about the more than 3 objects? Of course, there are two. If there are too many objects, still there will be a miss. But for the anchor box, can solve the problem of detect the overlapping objects. This explanation was from Andrew's video. Let me take a look of this, if this video is still exists or not.
What is the problem?
Okay, let me share the video.
With object detection, as you've seen it so far, is that each of the grid cells can detect only one object. What if a grid cell wants to detect multiple objects? Here's what you can see: the idea of anchor boxes. Let's start with an example. Let's say you have an image like this, and for this example, I'm going to continue to use a 3x3 grid. Notice that the midpoint of the pedestrian and the midpoint of the car are in almost the same place, and both of them fall into the same grid cell. So for that grid cell, if y outputs this vector, where you are detecting 3 classes, pedestrians, cars, and motorcycles, it won't be able to output two detections. So I have to pick one of the two detections to output. With the idea of anchor boxes, what you're going to do is predefine two different shapes called anchor boxes or anchor box shapes. And what you're going to do is now be able to associate two predictions with the two anchor boxes. And in general, you might use more anchor boxes, maybe 5 or even more. But for this video, I'm just going to use 2 anchor boxes just to make the description easier. So what you do is you define the class label to be, instead of this vector on the left, you basically repeat this twice. So you would have PC, BX, BY, BH, BW, C1, C2, C3, and these are the 8 outputs associated with anchor box 1. And then you repeat that, PC, BX, and so on, down to C1, C2, C3, another 8 outputs associated with anchor box 2. So because the shape of the pedestrian is more similar to the shape of anchor box 1 than anchor box 2, you can use these 8 numbers to encode that PC is 1. Yes, there is a pedestrian. Use this to encode the bounding box around the pedestrian, and then use these to encode that that object is a pedestrian. And then because the box around the car is more similar to the shape of anchor box 2 than anchor box 1, you can then use these to encode that the second object here is the car, and have the bounding box and so on be all the parameters associated with the detected car. So to summarize, previously, before you were using anchor boxes, you did the following, which is for each object in a training set image, it was assigned to the grid cell that corresponds to that object's midpoint. And so the outputs Y was 3 by 3 by 8, because you had the 3 by 3 grid, and for each grid position, we had that output vector, which is PC, then the bounding box, then C1, C2, C3. With the anchor box, you now do the following. Now, each object is assigned to the same grid cell as before, assigned to the grid cell that contains that object's midpoint, but it's assigned to an anchor cell, but it's assigned to a grid cell and anchor box with the highest IOU with the object's shape. So you have 2 anchor boxes. You would take an object and see. So if you have an object with this shape, what you do is take your 2 anchor boxes, maybe one anchor box is this shape, that's anchor box 1, maybe anchor box 2 is this shape, and then you see which of the 2 anchor boxes has a higher IOU with the ground truth bounding box, and whichever it is, that object then gets assigned not just to a grid cell, but to a pair. It gets assigned to a grid cell, comma, anchor box pair, and that's how that object gets encoded in the target label. And so now the output Y is going to be 3 by 3 by 16, because as you saw on the previous slide, Y is now 16 dimensional. Or if you want, you can also view this as 3 by 3 by 2 by 8, because there are now 2 anchor boxes and Y is 8 dimensional. Oh, and dimension of Y being 8 was because we have 3 object classes. If you have more objects, then the dimension of Y will be even higher. So let's go through a concrete example. For this grid cell, let's specify what is Y. So the pedestrian is more similar to the shape of anchor box 1. So for the pedestrian, we're going to assign it to the top half of this vector. So yes, there's an object, there'll be some bounding box associated with the pedestrian, and I guess if a pedestrian is class 1, then it'll be C1 is 1, and then 0, 0. And then the shape of the car is more similar to anchor box 2, and so the rest of this vector will be 1, and then the bounding box associated with the car and then the car is C2, so that's 0, 1, 0. And so that's the label Y for that lower middle grid cell, right? That this arrow is pointing to. Now, what if this grid cell only had a car and had no pedestrian? If it only had a car, then assuming that the shape of the bounding box around the car is still more similar to anchor box 2, then the target label Y, if there was just a car there and the pedestrian had gone away, it would still be the same for the anchor box 2 component, right? Remember that this is a part of the vector corresponding to anchor box 2. And for the part of the vector corresponding to anchor box 1, what you do is you just say there is no object there, so PC is 0, and then the rest of these would be don't cares. Now, just some additional details. What if you have 2 anchor boxes but 3 objects in the same grid cell? That's one case that this algorithm doesn't handle well. Hopefully it won't happen, but if it does, this algorithm doesn't have a great way of handling it. I would just implement some default tiebreaker for that case. Or what if you have 2 objects associated with the same grid cell, but both of them have the same anchor box shape? Again, that's another case that this algorithm doesn't handle well. If you implement some default way of tie breaking, if that happens, hopefully this won't happen in your data set. It won't happen much at all, and so it shouldn't affect performance much. So that's it for anchor boxes. And even though I motivated anchor boxes as a way to deal with what happens if 2 objects appear in the same grid cell, in practice that happens quite rarely, especially if you use a 19 by 19 rather than a 3 by 3 grid. The chance of 2 objects having the same midpoint out of these 361 cells, it does happen, but it doesn't happen that often. The maybe even better motivation, or even better results that anchor boxes gives you is it allows your learning algorithm to specialize better. In particular, if your data set has some tall, skinny objects like pedestrians and some wide objects like cars, then this allows your learning algorithm to specialize so that some of the outputs can specialize in detecting wide, fat objects like cars, and some of the output units can specialize in detecting tall, skinny objects like pedestrians. So finally, how do you choose the anchor boxes? People used to just choose them by hand, choose maybe 5 or 10 anchor box shapes that spans a variety of shapes that seems to cover the types of objects you seem to detect. As a much more advanced version, just an advanced comment for those of you that have other knowledge in machine learning, an even better way to do this in one of the later YOLO research papers is to use a k-means algorithm to group together the types of object shapes you tend to get, and if you use that to select a set of anchor boxes that is most stereotypically representative of the maybe dozens of object classes you're trying to detect. But that's a more advanced way to automatically choose the anchor boxes. And if you just choose by hand a variety of shapes that reasonably spans the set of object shapes you expect to detect, some tall skinny ones, some fat wide ones, that should work reasonably as well. So that's it for anchor boxes. In the next video, let's take everything we've seen and tie it back together into the YOLO algorithm.
Okay, so that's the introduction of anchor box from Andrew. It's the best explanation online. So it's almost time to take break. So let's take 10 minutes break, actually 12 minutes, and go back in 2:10. Thank you. Okay, so we have learned the anchor box. Let's back to the YOLO object detection. Okay, so how can we define the shape and the size of the anchor box? It's actually used on supervised learning. For YOLO v2, the authors running the k-means on the anchor box on the training data set. It should be the COCO data set, and find the most popular clusters. There are 15. I'm sure. But they select around 1, 2, 3, 4, 5, maybe 5 or I don't remember the number, but they still select several anchor box as default anchor box. Okay, so actually, because for the efficiency of most detector code are implement using C++, not Keras or TensorFlow. So it's not easy to find an example to demo the anchor box. But recently I find a very good resource. It's a free notebook from a deep dive into deep learning. Let me share the website. Okay, there's a very good online textbook which have introduced many important concepts in deep learning. Of course, there are so many free resources online, so it's only a matter of your understanding and time to learn all the materials. But this book is free and it has been written by many experts in this area. Looks like the expert in Amazon. Most of them are scientists in Amazon, and also a CMU assistant professor. And they include many code examples, but mostly use the PyTorch and MXNet. I still don't use MXNet. PyTorch and TensorFlow and MXNet. Okay, so yeah, you see they are showing bunny bars of Pikachu, and also they have a lot of math examples, mathematics and math examples. So I really like this textbook. I will add more material in from their textbook in our class next semester. So you are welcome to take my class again in next semester. Yeah. Okay. So you see they include some latest topic like attention mechanism or transformer. So let's back to their introduction to anchor box. Okay, anchor box. So they actually, I don't know why they use MXNet or what's MXNet, but they provide PyTorch. In this case, PyTorch is better to demo the flow, the architecture of object detection. So it first generates multiple anchor box by the code. So anchor box was applied to according to this textbook centered on each pixel. Okay, and they have a aspect ratio. Okay, so let's omit details now because also I don't have time to read all the details. But anyways, the code can generate a different anchor box here. But it assign a anchor box with different aspect ratio, right, and the scale, and it's generate different bounding box. And then I introduce the idea of intersection over union. To evaluate the performance of object detection, we use the intersection over union (IOU). Here's the intersection area under the total union area. Okay, so we use IOU to evaluate the accuracy. So to evaluate, we need to define a threshold to define that if it's detected or not. So we use IOU as a metric to evaluate the detect accuracy. Okay. Oh yeah, so we use IOU to measure the similarity between anchor box and the ground truth bounding box, and between the anchor box. Okay. Now is tell you how to label anchor box in training data, which is you can guess very difficult. So well, we can omit the details, but if you need to have a in-depth understanding of anchor box and object detection, now you can take a look at this. Take a look at this example. Also, Andrew's introduction video is pretty good. But this one with code. And yeah, and also it's said that PyTorch's vision library, computer vision library, like object detection, are more efficient than TensorFlow and more bug-free. Also, for industry now, they are using PyTorch for their industry applications, using PyTorch object detection or segmentation instead of TensorFlow. So although we didn't cover the PyTorch in our class, but they have many similarities with the TensorFlow. So you are encouraged to look at also. As you can see, there are many examples. So like this is like the SSD, or they introduced the SSD single shot on this scale example, and the region-based RCNN. And the semantic segmentation. Well, RCNN, okay. RCNN is too old, so. But the popular application is the mask RCNN, which can be used for semantic segmentation. It's more precise, more accurate than YOLO, because YOLO cannot be used for segmentation. Okay. Still, RCNN is more accurate than YOLO. Okay, so that's the anchor box tutorial. Okay, I lost my window. There are too many windows. Where I find the window again. So the backbone of original YOLO is the darknet. The latest backbone of YOLO has been switched to CSP.NET proposed by Dr. Wang Jianyao. Okay. So for ImageNet, For darknet used mostly 3x3 filters to extract features and 1x1 filter to reduce the output channels. So again, this use the trick to they use the trick of 1x1 filter to reduce channel size first. Right, on darknet. So darknet is implemented in C++. So to train an object detector, you need to use the darknet and the YOLO v2 provided by the author. Okay, another trick adopted by the YOLO v2 is the hierarchical classification, because there are too many objects. Objects, can be, there's a taxonomy of the objects, right? For Coco, there are around 80 objects. For ImageNet, it's actually more than 1,000, or it's around 22K objects. So we can use a word tree to first, roughly classify an object into animal, artifact, or natural objects or phenomena, and make a more detailed classifications. Actually, is a tree-like classification. Hierarchical classification, because the YOLO v2 intended to classify too many objects. But so far, it's still are good at identify only several objects, maybe around 10, I think. But it's enough for many applications, right? For detect pedestrians. I'm not sure if Tesla use YOLO, but yeah, YOLO can be used to detect many objects. It's very efficient. Okay, so here's the performance comparison of YOLO v2 with RCN1, right? So YOLO v2 has actually they have better accuracy than faster RCN1 on the Coco dataset. But of course, RCN is also keep improving. So the mean average precision is around 80, almost 80. The x-axis, the horizontal axis is the frames per second. The higher, the faster. So YOLO can, ignore more details and run much faster or achieve more around 100. I believe they have surpassed this threshold. It was released several years ago, so it can achieve hundreds of frames per second, which is very useful for real-time applications such as autonomous vehicles. Because for autonomous vehicles, we always want our response time as short as possible, right? So if we can run as many frames as possible, that would be very helpful. Okay, so for YOLO v3, as the name suggests, it's the incremental approach. They fix a bug and refine the training. So the average precision on Coco dataset, the previous one was one VOC 2007, was an old dataset. In this case, on the latest Coco dataset, the YOLO v3 outperformed other architecture, the RetinaNet, and where's RCN1? No, I didn't see it. Anyways, outperform SSD or other architecture. YOLO v3 inference time. And this is the inference time, or the shorter the better. So around YOLO is here, much faster than other architecture, but other architecture like RetinaNet has more accurate than YOLO. So the YOLO v4 just published last year by Wang Jianyao and Okavosky and Mark Liao Hongyuan in the Academia Sinica. They are from Zhongyuan, and this one is the maintainer. I remember he's from Russia. He's the maintainer of the YOLO v3, And the final backbone is proposed by Jianyao Wang CSP that is good for v4. So they published the paper together. So v4 optimal speed and accuracy of object detection. Right. So it's fast and have a very good accuracy. Of course, there are always some architecture that have higher accuracy, but slower. It seems like the most accurate one is the efficient net proposed by. Remember the efficient. It's called efficient detection. So one way to generate new detector is to switch the backbone of their underlying convolutional neural networks. So you can switch the CNN in the object detection architecture, right? So use efficient detect, it will have a higher average precision, but your v4 is still more accurate, much faster. So your v4 is faster, although not as accurate as efficient now. But I have a new publication this year. I think they are keep improving the architecture. And then this is an achievement. Yes. Sorry, I'm checking what's the difference. AP50. Maybe they select, sorry, I need to check what's AP50, but I think maybe they select only 50 more popular objects in this case. In this case, YOLO V4 is more accuracy, is more close to efficient detect. And then YOLO V4 is much more faster, much more accurate than YOLO V3. Much more accurate. Of course, our computing power has been improved over time. So we are more accurate now. So there are many new techniques adopted in YOLO V4, like weighted residual connections, cross-stage partial connection, and cross-mini-bench normalization, self-adversarial training, mesh activation. So YOLO V4 have adopted many new advanced techniques to train the model. But it's this is a hard work, right? Try so many different combinations and achieve high results, but turns out it works very well and achieve highest performance. As object detection is the most fundamental task in computer vision, this work make a lot of contributions for the world. Okay, another architecture is the single-shot multi-box object detection. As we know, the convolutional neural network will go through multiple scales, right? It will, for like VGG19, it will generate feature map at different scales. So the single-shot multi-box try to detect object at different scales on the feature map. So it's a single-shot multi-box. This is called multi-box. Here's the dimension of SSD. The original SSD used the VGG16, which has 5 convolution layer, and for each output, 3. I think for each block in the VGG, they use the top feature map, right, and try to run prediction on the using a final fully connected there. There's a for each class there will be around 8,000 possible detection multi-box on different scales. Remember, there are remember, our objects can be at any locations and at any distance from the camera, so it will exist in any scales. Right. So the SSD try to detect objects at different scales. Okay, so in the previous version, the SSD is more accurate for small objects than the YOLO. Right now, YOLO has improved a lot. Maybe they are, I think YOLO has employed a much multi-scale detection as well. Okay. Okay, so the key to detect small object is to use the feature pyramid. There's another architecture called feature pyramid. We will try to detect that object on the smaller feature, but the smaller object in the larger feature map. So there's multiple detections at different scales of feature map. And there's two approaches. One is top down, another is bottom up. SSD is actually a bottom up, so I need to check what does that mean, but I think that it used the upper layer in the block as a feature map and make predictions. So FPN use a top-down approach. Okay. Which means maybe they detect object first and then go down detect the potential region proposal and then go back to lower layers to find a more possible bounding box. But I need to check the details of FPN. FPN also has quite good accuracy, but now the most popular framework is YOLO. Okay, and also there's another loss function called focal loss. As we know, there's always an impedance problem on the data set of objects. Some objects are much more common than the others. Maybe the most objects in the label data set are humans. So we should use focal loss, which reduce the loss for well-trained class. Right? There are well-trained example like human, but we should focus on the other not accurate objects detectors. So we can use focal loss. It will multiply by the probability of predicting class probability for ground truth. So focal loss will help you to focus on the less popular class, less accurate class. Okay, another one is the retina net. Right, it's used something like top-down approach. Okay, but I'm not familiar with the retina net, so let's omit the details right now. So the other is the efficient detect, right, based on efficient net proposed by the efficient team. They use NAS to search the results. So the backbone of the efficient net is be optimized by the neural network search, but it was optimized by a computer. And they also use the feature pyramid there, right, and make predictions. So if you are interested in efficient net, you can read its paper. I think it's just published last year, but I forget to add the publication date, but I think it's just published last year. And also there's a PyTorch implementation of efficient net, and it's said that it's very much more efficient than even faster than YOLO. It can be as fast as it can be 25 more times more efficient than on TensorFlow, because efficient net team it's a Google team, so maybe they must use TensorFlow to implement. And some guy or some volunteer use PyTorch to implement efficient net. Finds much faster. If this is true, then it will be faster than YOLO. But let's wait and see. If this is true, I think efficient net will be more accurate and faster than YOLO. But I didn't follow up this post, so I will check again. Okay, so that's what it looks like to run efficiently. Now the latest detectors can detect small objects very well as well as very fast. Okay, so that's the result of efficient net. And also detect the overlapping object very well. Okay. Finally, let's briefly talk about the segmentation. As far as I know, the most popular algorithms, the mask RCNN based on, faster RCNN, but and the mask to predict the class of each pixel. So right now, inside the bounding box, you can see there's a prediction of the object's pixels. But until last year, the most popular implementation is made by Matterhorn, a company which is specialized in 3D imaging. Matterhorn has created a mask RCN trend, and it's only support your TensorFlow 1.3, which is considered old right now, right? So my suggestion is to switch to PyTorch. You can try PyTorch. Sorry, because the COVID-19 is pretty bad these days, so I didn't finish to try the new code. But you are free to survey the PyTorch segmentation code, okay? And then use the pre-trained YOLO, Microsoft Coco dataset to train the RCN. It's very difficult to label a segmentation image, right? You need to draw a very precise bounding box of the object, and then you can make a training for segmentation. So the most popular dataset right now is Common Objects in Context, or COCO dataset, made by Microsoft. Okay, here's a tutorial to train a custom object detector on Colab. You can try it. So that's it. That's today's class about object detection and segmentation. It's not detailed introduction. I omit many details about, and we didn't see many code. But I offer an overview, and I provide some good resource which you can study if you are interested in object detection. Okay, I hope in the future we can have know more details and see more examples in the class. Okay. Okay, so remember to register your final project. Register your final project and record a video for 10 minutes. All right. Name is okay. So remember to submit, to fill this form and submit. You can still try to find your members online. You are free to ask people to join your team on the FB group. Don't be shy. Just ask. And then each team can have at the most 5 members. But if you want to do your project alone, it's okay. And please prepare a 10 minutes video to introduce your work in English and upload the video to YouTube before June 13th. And I will make a web page, and each student need to watch others' video and vote score for each team, and your score will largely based on the average of other students, and also my score is a weighted sum of my my score and the average score from other students. Okay, so that's it. Thank you for joining today's class. I hope all of you are safe and stay safe at home, and hope this 19 will be passed very soon. Thank you. Class dismissed.